All right, guys, we got our last section to talk about with logarithms and exponents. So we're going to add pages 95 and 96. And we're going to talk about solving logs and exponentials. So this last one, that's just a goof. Don't know. Alrighty, let's turn to there. I always like solving so much because it's kind of the same every time. So on this side here, we'll talk about solving exponentials. And over here, we'll talk about solving logarithms. Okay, so let's start with solving exponentials. Basically, when we're solving, we need to get x totally alone. And the way that we get x alone is like we get rid of addition, subtraction, we get rid of multiplication, division, same thing every time. But there's always something new. And that's usually where we feel stuck, where we're like, what am I supposed to do next? So that's what we got to talk about here. So basically, we want to think about two things. We want to get our x alone. Now with an exponential though, our x is going to be up in an exponent. So we want to get our b to the x alone. We do this by getting rid of addition, subtraction, and then multiplication and division. Whenever I put this, I always think like division. Now there might be stuff up here with x, but you need to get the base and the x alone. Then you're going to probably feel stuck. Like, what do I do now? Because x is up in the exponent and I don't know how to get it out. So luckily, we have a logarithm that is the opposite of an exponent. And a logarithm has this really great property, the power property, that lets me take exponents out of the power. So like you take your power and you boop it out front. So at this point, when our base is alone, we want to take the log base on both sides. That's basically it. After that, you might have to finish up a few things, like clean a few things up to totally simplify, but that's kind of it. So we're just going to do a whole bunch of examples here. So let's say we had 2 to the x plus 3 minus 1 equals 7. I might sneeze, just warning you. So here is my base to the x power. We need to get that alone. So I'm going to add the 1. And so I'll have 2 to the x plus 3 equals 8. Now I could actually use one of my clever little properties here from the other day, because I could rewrite 8. Oh no. No? Is the light? Sorry. I might sneeze. I could rewrite 8 as 2 to the 3rd, and then we could solve that way. So that's one way to do it. But I do want to show you this new way. So now we would take the log base on both sides, because my exponent is alone, so I'd take log base 2 of both sides. That allows me to take the power out, and log base 2 of 2 is just 1. So we get our x plus 3 all by itself. And over here we have log base 2 of 8, which we know log base 2 of 8 is 3. And we subtract our 3's from both sides to get that x is 0. Which makes sense. Like if I plug it in right there, that would get me 8. I'm so sorry, I'm going to pull my nose. All right, let's try a slightly weirder one. So for example, let's say we have 10 to the x plus 7 minus 4 equals 10. Okay, so a lot like that last one, we want to add our 4 over, so 14. And now my b to the x, so my exponent is all by itself. So here's where we want to take our log base on both sides. So we take log base b, log base 10, both sides. That allows me to take my exponent out, and log base 10 of 10 is 1. So we have x plus 7 equals log base 10 of 14. Now this one is weirder because log base 10 of 14, like 10 to what power is 14? I do not know. Probably a decimal. And so if I'm not going to use a calculator, I kind of have to just leave it like this. But I do need to get x alone, so I'll subtract the 7. And here's the thing. This is some decimal, and then I subtract 7. I don't get to subtract the 7 from the 14. So without using a calculator, kind of my final answer here looks like log of 14 minus 7. Now if we do want to approximate with a decimal, we can pull up our calculator. And because we're base 10, we don't have to hit the second button, so we just do 14 log base 10, and that's that crazy decimal, and then we'd subtract 7. So approximately negative 5.8539, depending on how many decimal places we want to go. So yeah, let's try a couple more. Let's say, for instance, we have 7e to the 3x power minus 1 equals 13. Okay, so e to the 3x, that is my base, like it's the number directly below your exponent. So I need to get rid of the negative 1 and also the 7. Okay, so we're going to add our 1 for 14. Then we will divide our 7 away on both sides so that we have e to the x power all by itself equals 2. So now that my base is all alone, we want to take our log base on both sides, and when the base is e, we have a special logarithm, and that's natural log. So we do natural log on both sides. This lets me take the exponent out, and the natural log of e is just 1. So we have 3x equals natural log of 2. And again, one of those, so natural log of 2 is saying e to what power is 2? I do not know. Calculator time for that one. And then I divide by 3. So if I'm not using a calculator, kind of my final answer here is natural log of 2 divided by 3. But if we're going to approximate with a decimal, go back here, and we want to take the natural log of, what was it, 2? So 2, natural log. Then we want to divide by 3. So approximately 0.2310. Fun. Okay, let's try one more like this, and then we'll try some logarithms. So let's say we had 2 times 3 to the x plus 4 minus 1 equals 17. Okay, so we need to get our exponent all by itself, so we'd add the 1. And then we divide our 2. And here's where I would take the log base of both sides. But if I'm very clever about things, I might not have to. So like I notice over here that I could rewrite that 9. So I'm gonna. And make it 3 squared. And now that these bases are the same, I can use that 1-to-1 property. So I can just say, okay, x plus 4 equals 2. And so x is negative 2. So that's much easier if you're able to notice those things. Okay, I'm going to pause it here and I'm going to make a separate one for the logarithms.